research at Damballa where they detect malware by looking at network analysis and saying, hey, what's going on out there? Which sounds kind of neat. And we're talking a little bit about what he's doing and things like that. He used to be a researcher in the ISS type world and now getting his PhD at Georgia Tech. So smart guy, some really cool stuff. I'm looking forward to his talk, and I think you would be too. So without further ado, take it away.
Thank you. Yeah, thank you, and thanks for coming to my talk. So, like you said, I'm actually Director of Research at Damballa Labs, and so I'd like to start off and tell you a little bit about what we do and the type of research that we do at Damballa Labs. And so we really have two groups there. And so one, really a group of practitioners and another group of academics. And so the practitioners tend to really stay on top of things, and so they can tell me like the latest exploits that are out there, the tricks that malware is using to avoid AV, and they even dig in and look at the operators and who's actually behind the botnets and malware. The academics, on the other hand, tend to get to the bottom of things, so they'll like really zoom in and focus on a specific problem, dig into the details. But when they go and they theorize their solutions, often some of their assumptions may not be valid, and so this is when the collaboration with the practitioners are really useful because they can help validate the assumptions made by the academics and if it would really work in the real world. And then this goes all the way through prototyping. And so when we develop prototypes, we actually get those verified by the practitioners. Does it really solve a real world problem? And so to me, our research is really good when we have a combination of the inputs from the academics and the practitioners. Either if the research starts on the practitioner side or on the academic side, I think the best things that come out of Damballa is when we have this good collaboration. And so today, I'm going to talk about practical machine learning for network security. And I'm going to use a couple of case studies. And so at Damballa, we use machine learning and a lot of the solutions that we provide. And so I'm going to walk you through two case studies and show you problems that we faced using machine learning and applying it to network security, as well as things to like keep in mind as you try to apply this in your work. And so what I'm showing here in this diagram is basically the different steps that are typical in any machine learning project that we take on. And so actually, I'm going to walk through each of these steps and using those case studies to show you how we actually move through this process of applying machine learning to network security. And so I'm going to start with the data. And so data is fundamental to the success of any machine learning project. If you don't have the right data or you do not have enough data, your machine learning project will fail. And that's even if you get everything else right. So if you have an excellent data science team and they can go through the entire process doing everything correctly, it's still going to fail if you don't have the right data. And so often when you start a machine learning project, the first thing you'll do is ask yourself, what data do I need for this machine learning task to succeed? And once you've kind of answered that question, you can really go in into actually defining, well, what problem am I trying to solve? Or often you'll start off trying to define a problem and ask yourself, what data do I need? And so you really will need to allocate time in your machine learning project to go out and acquire this data, or build systems to either acquire it or go out and pay providers to send you the data. And then once you have the data, the next step is really going in and defining the problem you're trying to solve. And it typically starts off with like a very high level definition. In this case, I'm giving an example that we want to detect infected hosts by observing their network communication. But this in and of itself is not enough to apply machine learning to this. It's more like a high level goal. And so what we want to do is really look at the data that we have, or the data that we can acquire, and see, well can we define a data science problem or a machine learning problem from it. And so in the case of observing malware communication, this particular slide, as you move from left to right, it's signifying time passing. And so at the bottom, I'm actually showing the malware itself evolving. And so the malware is evolving because it's basically getting repackaged, recrypted with a new key, and it's continuously changing because it's trying to stay one step ahead of AV. At the very top, I'm showing the actual destination changing. So these are the command and control servers, and so their domain names, their IP addresses are changing, and they're doing that to stay a step ahead of blacklisting and takedown. And so if you start looking at this, you start saying, well, where could I focus on actually trying to detect this communication? And one place to do it is at the protocol structure itself. And so the protocol structure, if you start to analyze the data or the types of communications used by these malware, the actual structure of their communication seems to change a lot less frequently. And if you've ever written a client-server application and you actually have some clients out there talking to your server application, you know that's more difficult to change than say like we're a domain name point. So it's not that it can't be changed, it just seems to stay constant for a longer period of time. And so the first problem in our case study that we're going to define is CNC protocol detection. And so we really need to define three things here. First is the actual task. And so what are you trying to do? And in our case, we're trying to recognize and attribute CNC communications on live networks. And the next question you have to ask, well, how am I going to get that training experience for my learner? And so in this case, we're going to use packet captures of labeled CNC communication. And so where can we get these packet captures? Well, one thing, we can run malware in a sandbox. And we can observe malware execution in a sandbox and actually create packet captures from it. And then as far as labeling the data, we can actually age those packet captures, and as domains get added to blacklists, we can then go back and label the network communications to a specific malware family or botnet. And then lastly, you have to define like a performance measurement, because you have to really know if you're going to train or you're going to model network communication or any issue, you really have to have a way of measuring how is that learner improving. And in this case, we're going to measure that by looking at the percentage of network communications classified correctly. And classified correctly means identifying that it is CNC communication and identifying the malware family associated with it. So that's case number one. Number two is DGA-based malware. And so we're going to look for a specific type of malware infection, specifically infections that use a domain generation algorithm. And so this slide shows you basically how the DGA works. And so on day 0, it generates some number of domains using its DGA. And then it will go and it'll actually start looking up those domains. And there'll be a few that are registered. But in the process of trying to find the domain that is registered, it actually generates NX domains. And then on day 0, it generates some number. Then on day 1, it typically is a new set, and it repeats the process day 2, and it keeps going. And so one thing that really differentiates these DGA-based malware from like other applications on the network is the number of NX domains, and they're generating NX domains. And so that's another thing that we're going to look at, and we're going to model that and see, can we detect not only that a machine is infected with malware that is using a DGA, but also can we actually do the attribution to the malware family? And so that's task number 2. And again, we divide it into task, training experience, and performance measurements, as you can see. So once you have the problem defined, the next step is to engineer the features. And so this is perhaps the most critical part of any machine learning project is this feature engineering. And the majority of your time in your machine learning project is going to be spent here in feature engineering and in actually acquiring the data, cleaning the data, maintaining the data, the bulk of your time. And you won't spend that much time actually doing the learning or the machine learning piece, which is the next step in our process of modeling. And so in engineering features, this is where it really helps to have domain knowledge, and so to have that security expertise and really know what we should look for to actually provide the learner in modeling what we're trying to learn. And so it also requires like a lot of intuition and creativity, because it's typically not the raw data that you want to feed your machine learning algorithm. Instead, you want to perform some types of calculations on this raw data or transform the data in some way. And the other important thing that kind of separates machine learning and security from machine learning in other places is that we actually have an adversary that if they know your features, they may try to actively evade those features. And so when you're going through and trying to select features, you want to ask yourself, how easy is it for someone to bypass this specific feature that we're trying to model? If it's extremely easy, then it may not be a good feature for your modeling. And so I'm going to show you some of the features and the way we actually extracted features for both of our case studies. And so we'll start with the CNC communication. And our first step here is actually generalizing these requests. And so here you see, I'm showing two requests, request 1 and request 2. In request 1, if you look at these requests, you actually try to use like a traditional distance measurement, edit distance between the requests, how they are. They would be very far apart. But obviously, looking at these two requests, they definitely look related as far as the structure of their communication goes. And so what we'd like to do as a first step in our data is generalization. And so what we did is we went through and we actually recognized the data types and encodings that were in the communications, and we replaced the specific strings with those data types and links. And so in this case, the first part of this path was base64 encoded, and we have a link associated with it. The same for the values in the query string. And so if you see V and CC, we've actually replaced the specific values with an integer of link 3 and with a string of link 2. And so this is really the first step, because we didn't want to extract the exact strings because those are too easy to change. Instead, we want to really look at the structure of this communication. And so once we have that completed, we would then go and try to extract features from these protocols. And one feature that we looked at was the actual names that are used in the query strings. And so these names may not always be present, or they may actually be changed by the malware, but a lot of times the exact same name is there. In addition to actually using the specific string that we saw, we also do the same generalization process to these names and also look if the character sets for these names match a known malicious protocol. And so that's one feature. Another feature is actually looking at the values. And so we actually don't keep the strings and the values because they change almost request to request, or at least infection to infection. So we don't even worry about keeping the strings. We only keep the data types that we've observed in the communications as well as their links. And then another thing we look at is the actual path. And the same story here, right? We keep both the generalized parts of the request, so the actual data types and links, as well as the specific strings, because if we do see those specific strings in the protocol again, that could indicate a match. And then another feature, we actually look at the headers themselves. And so the malware typically doing command and control is not using the browser for its command and control if it's using HTTP. Instead, they rolled their own protocol. And so in this case, we would look and say, okay, well, what's the actual headers present in these requests? And so here we see host and user agent are present in both requests. We'd also look at the ordering of those headers. And so host comes before user agent. And then we'd actually look at the data in these headers. And so you can see we actually have a data type of hex for the user agent of length 8. And so that's the real protocol features used for the CNC detection. The other piece that we do, though, is we look at the host and we go out and we see, well, what IP addresses have we actually observed these domain names resolving to? And so we actually start associating protocols with networks. And so if we see a protocol that looks very similar to one that we've observed in the past, and it's going to a network which we've seen the protocol on before, then it can increase our confidence, as far as having a correct match. And so that's the actual command and control or the protocol side. On the DGA side, I'm actually showing domain names generated by two different DGA algorithms. So on the left, we have DGA1 and a sample of domains generated by DGA1. And so these would be NX domains on a given day. And then the same for DGA2. And so what we want to do with these is engineer features to detect and recognize DGA-based malware. And so one thing that we looked at is using n-grams. And so With n-grams, you can use unigrams, bigrams, and trigrams. And in this case, we actually use all of those. And what you're really trying to measure here in these domain names is like the character frequency. And so, unigram is measuring the frequency of a single character in these domain names, and bigram is 2, and trigram is 3. And so what we're really doing is trying to get the distribution of the character sets between the two DGAs. The next thing we look at is entropy. And so what we're trying to measure is the amount of randomness found in the set of NX domains. And so I'm not going to go through the formula for actually calculating the entropy here, but what I want to show you, and you can get this just by looking at these domain names, is that the ones on the left, tend to have less random looking domain names, right? Because if you look at the very top domain, it starts with FGA, and so do the next few. They all start with FGA. And then if you look just below that, we have some that start FVO, and all of them seem to have a dash, in the middle of their names. And so if you really measure entropy, you get DGA domains generated from DGA on the left does have a much lower entropy than those generated on the right. So that's another feature. Another thing to look at is the actual structural components of the domain names themselves. And so here we could look at the actual links of the names that are generated, as well as like the effective top-level domains the different NX domains are going to. And as you can see between DGA1 and DGA2, there are both difference in links as well as the actual effective top-level domains. And so these are some of the structural features. And then we could actually take a totally different view of DGAs. And so we could actually look at DGAs by the host that are looking up those NX domains. And so that's what this slide shows. It shows a matrix of NX domains as the actual rows, and the hosts are looking those up as the column. And each individual cell, it has a 1 in it if that host looked up a particular domain, and a 0 in it if that host did not look up a particular domain. And the idea here is that hosts that are infected by the same malware that is using the same DGA, they will look up overlapping sets of NX domains. And so it's another way, another feature to actually use to model different DGAs. And so once you've determined what features you want to use, how do you go about determining what features are important? Because you may have had a lot of great ideas and you think all these things are important, let me put all these things together, and I should be able to separate out these different DGAs, or I should be able to separate out these different malware families that are using these different protocols. Well, there are a couple of ways. If your features are small, then you can try all combination of features. So you can start out with basically 0 features and then try all pairs of your features together, and then you just keep going up. The only issue with using this technique is that it requires 2 to the n, where n is the number of features, tests in order to actually determine which features are important. And so it's not always feasible, because as soon as n gets fairly large, you can no longer use this method. But at the same time, you'd really like to eliminate some of the features, because basically the more features you have, the more difficult it is for your algorithm to actually generalize, because that's the real goal of machine learning, is generalization. So you really want to only include the features that are important. And so if you have more than some number of features that makes the first one infeasible, then another way of doing it is through forward selection. And so with forward selection, you basically start out and you train a model for each feature that you have individually, and you pick the model that gives you the best predictive power as an individual feature. And then you keep adding on. You go up to 2, 3, 4, always adding the feature that gives you the best results. And you wouldn't add features if they didn't improve the accuracy of your classifier. And then the last way is basically the opposite of forward direction. You actually start out with all your features, and then you remove the feature that gives you the least detection accuracy. Anyway, so that's the way you go about selecting features, and some ways to determine which features are important. But once you have those features, the next step is to actually do the modeling. And so this is where the learning happens. So in machine learning, after you actually have taken your data, engineered your features, that's when you go into actually do the learning process. And so there's a couple of different types of learning that you can apply. But the two most common that you'll find in network security is supervised and unsupervised learning. So in supervised learning, you basically have the labels for all, in the case of the EGA, we actually have the labels for all the NX domains that were generated from a particular malware family. So we're able to go in, label all the data, and then use the supervised learning method to then go in and actually figure out how to recognize this particular malware family based on its NX domains going forward. And so the left-hand side of this slide actually shows like a linear-based classifier and kind of how it's divided the space so it could recognize the different malware families. On the unsupervised side, I'm using the same data here on the unsupervised side, but the real idea is to use those features to actually group NX domains. And so in this case, you can actually see there it looks like there's 3 clusters, and these 3 clusters represent malware family A, malware family B, malware family C. But when we did the clustering, we didn't have any labels. And so we didn't have any idea as to what these clusters meant or if they were really related. And so what you have to go do on the unsupervised learning side is once you have these clusters, you dig in and you go through and say, can I label this data? Can I make sense of this data? And if you can label the data, you can then take these labeled clusters, and then they become the training set for your supervised learning algorithm. And so in the case of the command and control, in the case of command and control detection, we start off with unsupervised learning. And so we start off clustering HTTP requests. And so what this slide shows, the dots on this slide represent individual HTTP transactions. And these are transactions, like I mentioned before, that we've actually observed malware perform by running that malware in a sandbox. And so the circles are the clusters themselves. And so if dots are in the same cluster, that means those transactions were related. So we used our features, we did the measurements, and if we end up with 2 dots in the same cluster, it means it appears that those protocols are related. And so this is the first step that we do, because going forward, all we've had is these are these requests from malware executed in the sandbox, and this is the first step of clustering those requests. And then the next step is, okay, can we label some of these clusters? And can we do it automatically? In some cases, we can, because what we'll do is we'll go through each transaction in the cluster and say, do we know anything about this particular transaction? For example, by looking at the domain name, is this domain name on a blacklist? Is it known to be a CNC domain? If it is, then we can label that entire cluster based on the malware family associated with that command and control domain. However, even after doing that, there's going to be unlabeled clusters, and I have unlabeled clusters on this slide. And the next step at that point would be, okay, now can we go in and manually review these transactions in these unlabeled clusters? And what you would do is you'd go in and take a look at some of the requests, and if you could label 1 or 2 of those requests, then you could propagate that label to the entire cluster. And so some of these clusters have hundreds or even thousands of requests in there. And so it's a good use of time, right? You can go in and you can inspect a couple of these requests, and then you can propagate that label to all the requests within the cluster. But once we have the clusters labeled, either by automatically looking at the domain names or by manual analysis, the next step that we do is we find the center of these clusters. And the reason we find the center of these clusters is that we want to learn this. We want to remember these centers, because we're going to see communication in the future, and we really don't want to go through this complete clustering process again, because it takes time to do unsupervised learning. It takes time to clustering. So if we see a new request, what we'd like to do is ask the question, is this request close to any of these clusters that we labeled from before? And if the answer is yes, then we can say this new request should have been a part of that original cluster. And so this is what we actually learn from this process. We extract these centroids, and they become what we use to identify malware infections. And so we really need 2 things to use those centroids to identify infected machines. One is similarity. And so we want to measure, we see a new request, we'll extract the features I mentioned before, and we'll actually measure their similarity to these known CPTs that are associated with the protocol for a malware family. So we'll see how close does this request that we're observing look like what we've seen malware do in the past. And the other thing that we have to look at, though, is specificity, because the problem with just measuring similarity is that, for example, if malware within the path was doing a get to like / index.html, just because we observe a user going to /index.html does not mean they're likely infected with malware. And so what we really want to look at, besides just similarity, is also specificity. And so by specificity, we're saying, how unique is this particular protocol structure within the environment on which we've actually deployed this CPT? And so those are the two components. And so to get a high match score, we need both similarity and specificity to be high. On the DGA side, going back to it, I showed basically two separate views for clustering DGAs. One view was basically looking at the structure of the domain names that DGA1 and DGA2 generated, so measuring features from that structure, such as engrams. And then I talked about another view where we could go and we could look and say, okay, let's look at what the hosts that are generating NX domains, let's see if they're generating overlapping NX domains. And so those are the two views. And we actually do two separate clustering. And so we actually cluster based on the structure of those domain names, and we cluster based on the request hosts are making that they have in common. And so we do both because we start out using just the structure, and we start out, and then we actually try just using the host view. And we found that neither view gave us what we wanted, because both views, we had too much noise in the resulting clusters. And so what we found is if we take the approach of doing both, and then for the clusters that they generate, we go through and we pairwise look at the intersection between all clusters, and only keep clusters that have a large intersection, we can dramatically reduce the noise. And so that's what we do, is look at both views. And then once we have the clusters, we then go through and we can label the clusters. So we can look at the domain names and make a determination, well, what malware family generates those domain names, because we actually may have malware samples in-house that we've observed generating similar structural looking domains. And so here I'm showing we've actually labeled those two clusters, and so we labeled DGA1 as malware family A and DGA2 as malware family B. And once we have those labeled, those clusters labeled, they then can be input to a supervised learning process. In this case, we're going to model the DGAs based on those structural features. And so the resulting of this modeling is a classifier that can recognize and tell the difference between these two malware families by the DGAs, or the NX domains that they generate. And so this slide, I put it there just to list some of the actual modeling tools that we use. I'm not going to go into details of how these work, but these are probably the most common tools that we use at Damballa for doing machine learning and network security. And so I definitely recommend checking these out. There's other great tools out there, but these are the ones that we use. And so the modeling piece, is actually fairly easy because of these tools. Like I mentioned before, the feature engineering is simply much harder. Getting the data you need. The modeling, because of these tools, is relatively easy and doesn't take as much time, because it really lets you don't have to have a favorite model. You don't have to say, hey, I like support vector machines. Hey, I like random forest. Instead, you can actually go through and you can try all those different types of models on your features and see which one performs the best. And so the modeling has been made easy, much easier because of tools like those on the slide. And so once you have your model, the next step is to really do the evaluation. And so the key to the evaluation is, does your algorithm generalize? And so you've had this training data, so you collected all this labeled data, and what you're trying to ask is, hey, it works well. I was able to train a model that has good accuracy on the training data, but how well will it perform in the real world? And so you really need a different test set. You really don't want to try to measure your accuracy based on the training data. So instead, you need a separate data set. And so the way we did this with the CNC evaluation is we actually deployed our model on several real networks. So we deployed it on 2 university networks and a financial institution. We started actually generating CPTs from our samples 2 weeks prior to the actual evaluation, and then we ran the evaluation on these networks for 2 weeks. And here are some of the results from that. And so this slide is showing on the x-axis the number of unique CNC domains we discovered, and then the x-axis is showing the match threshold. And so the higher the match threshold is, the higher that similarity and specificity had to be for us to say a match occurred. And I also labeled the percentage of false positives for each one. And so as you can see, as we actually increase the match threshold, obviously the number of CNC domains we're able to detect goes down, but so does the false positive rate. In fact, at that 0.84 match threshold, we didn't have any false positives within our data. But this is a typical trade-off in machine learning. If you're trying to switch a lever and you're trying to determine the trade-off between your true and false positives, as you try to decrease your false positives, your actual true positives also go down. But how well did we generalize it? So was our assumption true that we could actually go through and find new CNC domains that were not on any blacklist? And so we actually had extracted those CPTs, and we knew the domains that were on the blacklist that we were using. We applied this to the network. And so you can see at University A and University B, over 50% of the detections that we had were actually new domains. So those malware families had actually switched to a brand new CNC domain. It wasn't being detected on that network, and the CPT was able to recognize the protocol, even though they had switched domain names. And then on the financial institution, we actually discovered some infections that they were not aware of, using the classifier. And so this is the results. In addition to being over 50% of the domains were brand new, over 90% of the infections on both University Network A, University Network B that we found were going to these brand new command and control domains. And so that's one way to do the evaluation, is to just apply your algorithm to a live network. Another way to do it is to actually to divide your training data. And so one thing you could do is if you had a large amount of training data is from the very beginning, make a split like 70-30 and exclude 30% of your training data for testing data in the future. But typically, you don't have the luxury of having a lot of training data. And so it may be infeasible to actually divide your data up front. So instead, there's this idea called k-fold cross-validation. And so what you do is you basically iterate over your training data, reserving a percentage of it for training and then a percentage of it for testing k times. And so the most common k is 10. And so, so in this case, I actually divided the training data into 10 equal sets, and we'll start out, on the right here, using that for our testing data, and then we'll train a model, and we'll actually use that data for testing, and then we'll train a new model, and we'll take another tenth of the actual training data and use that for our testing data, and we keep going all the way till we've done it 10 times, and we're back where we started. And so you actually built 10 models, and you've used different testing data each time, and the training data has been reused 9 out of the 10 times. And what you do then is you would actually average your true positives and false positives over all those training and testing. And so this is the result. So we use tenfold cross-validation for the DGA classifier. And so you can see we had several botnets that use DGAs, as well as a benign set, so it was non-malicious domains. And you can look here and you can see the actual true positive and false positive rate. So the supervised classifier is working fairly well. And so on the true positive rate, it means if we had the data component, if we had the data labeled as that particular botnet, the classifier also labeled it as that particular botnet. The false positive rate means that that particular labeled sample was labeled as a different botnet, but classified as the one on the row. And so the results look pretty promising, for our supervised learning classifier. The other thing that we evaluated, though, was the DGA clustering. And so how well did the DGA clustering work? And we deployed it at an ISP environment. And so what we found were 6 confirmed DGA-based malware, and so that top 6, we actually were observing NX domains, and we clustered those NX domains, and then we're able to manually label the clustered NX domains based on botnets that were known to use DGAs. We also discovered 6 new DGAs at the time of testing. And so these 6 new DGAs, we didn't know, we weren't aware of the malware families that were generating those particular NX domains. We've since labeled these and confirmed that these really were new DGAs, but at the time we discovered these, we didn't have malware samples for them. And so we discovered it just based on their DGA generations. And so once you've done the evaluation, the next step is to really deploy your technology. And so the way that we deployed the command and control detection, today we basically look at all of the, we have several malware feeds as well as getting malware from customers, but we run this malware in sandboxes, we look at their traffic, and we use our CNC, or our CPTs from our CNC detection to go through and match this traffic. And we're able to eliminate the majority of the protocols that we observe from our sandbox. However, there's some that we do not find or do not recognize. And so the ones that we do not recognize, they go through that language learning process I talked about before. And through that language learning process, we're clustering all the requests that we couldn't label. And then from that, we generate brand new CPTs. And so we extract those centroids for this new communication. And then these CPTs get deployed. And we basically, for the network they're deployed on, we use that similarity and specificity to measure each component of the CPT to see if the request that's being made from that network looks like a protocol that we have associated with the malware family. And if we do have a template match, then we say that the host making the request is infected, and we can actually say what malware it's infected by, and we can also extract the actual the actual domains associated with those requests and say that those domains are new CNC domains for this particular malware family. And so that's how we deployed the algorithm after going through the machine learning process. And then on the DGA side, we do kind of the same trick. So we look at NX domains that are being generated on the network. We send those through a DGA classifier. Some of those, or a lot of those NX domains we can actually classify. And if we can classify it, we can say that host is compromised with a specific malware family. And tell the user of the algorithm, hey, you need to go clean up that host. On the other hand, if we're unable to actually match, we then send that to our NX domain clustering. And so we go through that learning process I described before. We go through and we actually cluster these NX domains. And the result of an NX domain cluster or clustering are those clusters. And then we manually go through and label those clusters based on the domains that are within those clusters. And then once they're labeled, we can then feed those to the DGA modeling process, and then they go back out into a DGA classifier. So this is how we keep the learning ongoing, because you just don't learn one time, but in a machine learning process, you need to continually learn as things evolve. And so, lastly here, so this is the actual framework that we went through today. And it's a very iterative process. And so I know we went through it very linearly, and I stepped through each individual component of the process, but the projects never work out like that, right? And so that's why I'm showing the double arrows between these different components. And so, you would never go straight through. In fact, a lot of times when you go do your feature engineering, it's when you realize, hey, I need data that has these features that we're not currently collecting, and that may put you all the way back to the beginning of saying, okay, I need to go out and somehow acquire this data. And then the other thing I wanted to say is that I really see machine learning as a useful tool in network security. I think a lot of companies these days are really hyping machine learning. A lot of times they'll tell you their products work just because they have machine learning. But I think it's important to go back and ask them some of these questions. Say, hey, well, tell us about the assumptions and what problem are you really trying to solve, and tell us where you're getting your data and what features are you using, because that's really a very important part, more than the actual modeling itself. It is determining those other things, and with that, I'd like to say thank you. And there's two papers that I used, for the actual 2 case studies. And so if you'd like to go and get more details, about either project, that they were both published at Usenet Security, and one was called ExecSent, that was the command and control domain, and then there was another one called Pleiades, and that was the DJ detection. So you can really go through and read those papers and see the details and all the features and exactly how we use those to build both of those systems. And so that's the end of my presentation. I'd like to take questions now if you have. Yeah.
So the use cases you presented lend themselves to one classification models. Have you empirically observed any useful application of regression models to anything in security?
Yeah. So the question is, I presented really like 2 classification models, and so there's really several aspects of machine learning. Today we're actually talking about classifying, between one botnet and the other. He's asking, are there any applications to regression? And so that's not just predicting something as a certain class, but actually predicting a value for that class. None of the projects that we've done at Damballa so far have used regression, but I wouldn't rule it out. I would always keep that as a tool in my toolbox, but we haven't done anything that needed regression. Thank you. Question?
Have you run this model on any domains that aren't just responding with NX as non-existent domains?
Yeah. So the question is, have we used the DGA model or the DGA classifier on any domains that are not DGA? And the answer is, the way the actual DGA classifier works, it needs actually a set of NX domains. It can't just look at one NX domains, because the features that we're using, it needs multiple NX domains. And so in the paper, we actually talk about, well, how do you find the real domain? Because if you have a DGA, it's only going to generate NX domains for the domains that were not registered by the attacker, but they're going to have one legit request, right, that they actually make their connection to the live CNC domain. And we actually tried to use an HMM model, a hidden Markov model, to try to detect that. So we've done some work, in trying to actually detect individual domains, but it's not as successful as being able to just look at the NX domains themselves as far as classification goes. Yeah. Question?
You talked previously about analyzing HTTP headers and pocket payloads. How does encryption affect you?
Yeah. So on the actual protocol analysis side, yeah, sure. The question is, in your CNC protocol detection, if they're actually encrypting their data, how does that affect the modeling itself? And so there are really 2 things to that. One is that we really don't see a lot of encrypted CNC communication in our data feeds. I don't know if it's because of getting the certificates and having to change certificates, or or other things around that. The other thing is, like, a lot of our customers, what they end up doing is they're doing SSL man in the middle, and so they end up feeding the decrypted data anyway through our system. I don't know how people feel about that, but anyway, so those are kind of the ways you get around it. You're either doing SSL man in the middle, or either you're happy detecting the ones that aren't encrypted, right? Because it's a smaller amount.
Are you saying that a cell man in the middle doesn't actually help you a lot because most of it is not encrypted anyway?
Yeah. So in the data that we get, by far the majority is not encrypted. There is some that is, but by far the majority is not encrypted. They're actual CNC communications that we see. Yeah, question.
So one of the advantages I see with machine learning is that the system can sort of do its thing, and over time, how much time or investment do you see in adjusting the model
Yeah, sure. So the question is, machine learning could save you a lot of time, but how much time is really spent in prepping the models, getting the models ready, actually doing the classification piece? And so the answer is, the bulk of your time is not spent in the modeling. You have to spend some time doing the modeling, but usually it doesn't take that long to get that part right. What really takes a lot of time is the feature engineering and acquiring the data and labeling the data, because the majority of the supervised learning algorithms, you need to go through and like manually label that data, and that can be very, very, very time consuming. Once you kind of get a system bootstrapped and actually learning and actually doing the clustering that we talked about, it becomes a little bit easier, but still we do spend time, like in the case of the DGAs, right? We get this brand new cluster of index domains, and we haven't seen it before, and we have to have someone go through and take a look at those index domains and say, hey, can I link this to a known malware family? And if they can, then we can use it in our supervised learning algorithm. So really it's the labeling of the data, and then if you need to change your features for whatever reason, that take the longest. Any other questions?
Yeah. You seem to be pretty good at determining a specific family of malware.
Yeah.
You can generalize it to say, this is some kind of malware versus this is benign. So it would catch things that you have specific when you train on, but also what you've never seen before you never trained on.
Yeah, so that's really a harder problem, right? In a way, because there's not really anything that makes a protocol malicious per se, right? Or makes a specific index domain malicious. And so we find it's actually easier to try to go all the way and model a specific malware family, both on the DGA side and on the protocol side, just because there's not this thing that says, hey, it's malicious. Are there any other questions? What question?
Talk about structural modeling of like identifying various data types. Have you also looked deeper and maybe tried to like see if the domain matches some kind of natural language stuff that can be recognized?
No, we haven't. I mean, so the features that we engineered for on the DGA side seem to work well, and we haven't needed to change those. So we haven't tried to look any deeper in that because we have a working classifier. But it's definitely something to keep in mind if the DGAs evolve, in the future, it could become another feature that we use. Are there any other questions? No? Well, thank you.
Thanks, everybody. Next talk will be here.